This is Hakaru from the Ultimate Computer Scientist, and in this video I'm going to be talking about the architectural differences between Pascal and Turing. So you should all know by now that Nvidia has recently released its new Turing architecture, Nvidia's first new real architecture since 2014's Pascal release. Nvidia's target with Turing architecture were two things: ray tracing and AI development. However, AI is mostly relegated to the Volta architecture, of which it would appear that Turing was heavily based upon. I will also quickly be looking at the Vega architecture from AMD, mainly because Turing and Volta actually have a fair bit more in common with AMD's architectures. So let's start with the basics. AMD's graphics architecture is called GCN, that's Graphics Core Next. It was released in 2011 and has since seen incremental updates. Vega is a 5th generation of GCN. Next, Maxwell was released in 2014 with a GTX 750. However, it was changed a fair amount for its re-release with the GeForce 900 series. Then went on to TSMC's 16nm node, becoming Pascal. I'll be referring to these architectures as Pascal. So let's start with Pascal. Those GPUs have got 128 CUDA cores per SM. GCN is using 64 stream processors per compute unit. What this means is that one Pascal SM is equal to 2 GCN compute units. So looking at the GTX 1060 with 10 SMs compared to the RX 580's 36 compute units doesn't mean to say the RX 580 has almost 4 times the compute hardware, because the 1060's SMs are twice as big, meaning the 1060 actually has 20 equivalent compute units. Another thing about Pascal architecture is that it has a very light SM front end, with very lightweight schedulers and dispatch units when compared to the front end of GCN's compute units. Nvidia's Pascal and Kepler based GPUs have the instructions from the game renderer scheduled by the driver, where AMD's drivers are very lightweight, just compiling the renderer code and then dispatching them to the card. Because of this, AMD is able to do true asynchronous compute because there are hardware schedulers in the compute units that are able to co-schedule different work items together, much like done in a CPU. Also importantly, this means that AMD's GPUs can execute integer and floating workloads together. Now, however, the Nvidia's driver can't get low enough to the GPU hardware to be able to schedule work items asynchronously. Therefore, Nvidia uses preemption techniques, which means that when another work item wants to be executed, it's not done asynchronously. It's executed by halting the current thread and starting a new one. This means that if a Pascal GPU wants to execute a bunch of float workloads and then a bunch of integers, the floats will have to stop first before the integers can start. Not only this, but there is a penalty when switching between two threads. One thread has to stop, release its resources, and then the next one is allowed to be allocated its resources and start. This causes additional latency, which is why Nvidia has never made any gains from async compute. Pascal did make some improvements to the preemption over Maxwell, so Pascal did always lose less, if not lose any performance as a result of asynchronous compute when compared to Maxwell. The big takeaway from this, however, is Pascal is incapable of co-executing floats and integers. Also, remember, this architecture has 128 CUDA cores per SM. Now, turning to the Turing architecture, we can see that Nvidia has made an architecture arguably closer to AMD's GCN than Pascal. First, Nvidia touted Turing to have a new SM, which is said to give a 50% improved performance per CUDA core, whatever that means. I say that because Nvidia states, quote, achieving 50% improvement in delivered performance per CUDA core compared to the Pascal generation, unquote. Note the phrase delivered performance. This means that the different clocks of the GPUs tested were a factor in that 50% number. Nvidia claims two other main reasons for that 50% improvement in CUDA core performance. 1. Nvidia has added a separate integer pipeline, thus the ability for co-scheduling and co-processing asynchronously of both integer workloads and float workloads. This means that for mixed workloads, Turing would perform better than Pascal in all other things being equal. They did this by taking a massive amount of the Volta architecture's backend, with the Turing SM having 64 FP32 and 64 INT32 units. Nvidia has gone the way of AMDs GCN with compute units that have 64 asynchronous float and integer pipelines. This added ability to process ints together with floats have had one of the largest contributions to that 50% performance increase that Nvidia talks about. But how much did it contribute to that 50% number? Well, looking back to the Turing white paper, Nvidia claims that over their tests, quote, across several modern applications, we typically see about 36 additional integer pipe instructions for every 100 floating point instructions, unquote. And so, quote, moving these instructions to a separate pipeline translates to an effective 36% additional throughput possible for floating point, unquote. Now this is interesting to know, because not only does it mean that Nvidia reckons that 36% of that touted 50% shader improvement came from parallelizing integer and floats asynchronously, but also Nvidia uses hardware scheduling techniques from Volta. Remember, Turing is mostly made of Volta, and this allows Nvidia to utilize asynchronous compute for integers and floats. But don't take it from me, so take it from Gamers Nexus's review of the TitanV, saying in their conclusion of the article, quote, asynchronous computational pipelines appear to process more efficiently on the TitanV, unquote. I'll leave a link to the article if you want to look over their benchmark results for yourself. So we know where 36% of that 50% delivered performance came from. But what about the rest of it? Well, Nvidia claims a new memory path, or hierarchy, which will, quote, unify shared memory, texture caching, and memory load caching into one unit, unquote. They claim this will increase the L1 cache bandwidth and over double the L1 cache capacity for mixed workloads. So what does any of this mean? Well, Nvidia claims that of the 96 kilobytes of L1 cache, 64 kilobytes is usually partitioned off for shaders, and 36 kilobytes for textures, and Nvidia wants to merge the L1 cache altogether. Nvidia claims that this is the second major reason why Turing gets that 50% performance improvement per shader. So what do we know so far? Turing has the same number of execution units per core as AMD's GCN architecture. They've now introduced async integer execution like GCN. So does it show? Yes, it does. Looking at the benchmarks, it's clear that Turing is performing the best in AMD-sponsored games. Any surprises there? So what else was changed for Turing? Well, the SMs were also given the tensor cores, which allow these GPUs to utilize Nvidia's DLSS anti-aliasing technique. They also operate the denoising technique used to clean up the ray-traced sections of a scene, which bring me to the RT cores. These cores sit inside of the SMs, being one of the reasons for the massive increase in the size of the SMs. Also, another new shading technique that Nvidia is supporting are the variable rate shaders. This is where a shader can be run as little as once per 16 pixels, or as much as 8 times per pixel. This has the ability to save rendering times, as it means that in a region with low detail, a shader can be worked over a large amount of pixels, which will lose information, but means the shader only runs once. In areas of high detail, the shader can be executed multiple times per pixel, which will resolve the colour of that pixel most accurately. So what else do we know? Well, Turing really is a development of the Volta architecture, with Nvidia moving closer to AMD's GCN architecture as it provides the better asynchronous support. Although GCN is still able to co-schedule and process floats together where Turing can't, but is a step in the right direction. They also moved to 64 execution units per core, half of that of Pascal, and the same as GCN. I feel like this was to double the number of threads that the architecture can operate on, just with half the number of execution units on a thread. Also, Turing has the new RT and tensor cores. There are these in every SM, which seems to be the reason for the absolutely enormous die size increase. This increases the cost of the GPU, by making Nvidia only able to get up to 73 2080 Ti dies per wafer, compared to the 121 1080 Ti dies per wafer, meaning Nvidia is getting around 60% the number of dies as from the 1080 Ti with the 2080 Ti. Not only that, but the 2080 Ti uses GDDR6, although the 1080 Ti uses 12 GDDR5X modules compared to the 11 GDDR6 modules, so who knows what the cost difference is there. Now looking at the manufacturing process, it's produced on TSMC's 12nm process. Now don't be fooled by the name, this is the same process as the 16nm process, however it has got a larger reticle limit, that is, the maximum die size that the process can fab. This 12nm process gives no performance, density or power improvements as a result of the change, therefore clock speeds haven't moved. Well, that's it for this one. Researching this one has been a bit interesting. I didn't really look with much detail into the other GPU architectures too much, because I was just covering Turing, Volta, Pascal and Vega, and I only wanted to look at just Turing. I might do a more direct look into the other architectures, each on their own video, for more details later, but that's it for now. Anyway, I hope you've enjoyed and learned something.